All right, recording now. You can, I know, okay. Here, I have to share over here. Your selfie has to be from today to November 14. You cannot take a picture from, like, use a picture from last year. The idea is you go out, have fun, see if you can do it. That gets you 5 points. So that's the easiest 5 point, or maybe the most difficult, please, just like that, okay, to get. All right. Some of you asked me about natural frequency of the system and natural damping ratio, what they are. You probably didn't have control, or it's been a while. The CP21, which is due this weekend, I'm asking you to calculate natural frequency and damping ratio of a system. So I'm going to go over it very quickly. So it's a fair game, everyone knows what they are, so you can do your class participation. So another review. So we have two kinds of systems when it comes, so we model our system with mass spring damping, all right? We have discussed two different systems. You can have conservative system. It includes, when you model the system, it's a spring and a mass. So there's no friction and you're moving in some direction. So this is linear. You could have the same thing with rotational. All right, I'm just using linear example because it's easy. We have to find the dynamic equation or equation of motion of our system. You can use Newton's law. Very simple. You already know what it is. I'm going to use Lagrange very quickly. So as a reminder and show you we get the same solution. So from Lagrange, we can write our kinetic energy is 1/2 mx dot 2. So this is kinetic energy. And then our potential energy, I'm using with V, showing with V because I've been doing that last class, 1/2 kx squared, which is potential energy due to spring, due to the spring. All right, now following Lagrange equation to derive the dynamic of our system is going to be potential x, but we know this is mx double dot. If you put all of those and solve, you get here equal to negative kx, which is mx double dot plus kx equal to 0. You could do that by drawing the free body diagram of your m, right? So there is a kx negative to the other way because it's opposing the motion, and you have mx double dot moving the object toward x direction, right? So we could do that too. I'm just going to show very quickly. So from free body diagram, so there is a mx double dot going this way, negative kx opposing, but if you put this equal to 0, you'll get the same thing. So you can use both approach. This is more elegant and you can extend it to a robotic system. So that's why I keep using Lagrange equation. All right, so now we have our dynamic. So this is the equation of motion. If you write it this way, plus k divided by mx, so the coefficient of your x is 1, so that's what we're trying to do, equal to 0, then the coefficient here is going to be the natural frequency of the system. Called, bless you, omega n. But here we will use omega n squared, x equal to 0, then omega n would be a square root of k over m. So this is for your system. We don't have any controller yet, right? This is for any system. So if you can model your system to a mass and a spring, so behavior of the system, right? If you can model a mass and spring, then natural frequency is driven from here. And this is a conservative system. So we don't have any friction. So a lot of time we can say we can ignore the friction because it's too small with respect to the rest of the dynamic behavior. But what if we had friction or something that would oppose the velocity, right? That is dissipative system. When we can model a system using a spring, a mass, and a damper, or friction, right? So friction or damper, whatever that opposes and damps the motion of our system. If we do that, so we can say that this F, this force, will oppose the velocity. We can, following what we had in the last lecture, we can say this is negative sum coefficient times velocity, right? That's what the damping force comes from. So this opposes, if you remember, we used this to develop our D part of our controller, right? The derivative, we use that. So we can write d to the dt of k minus v x dot minus k minus v x is friction, or whatever is opposes your system, right? Or use Newton's law, you will get the dynamic to be mx double dot plus bx dot plus kx equal to 0. So this is because of your spring, this is because of your damping, and this is the inertia, right? We are going to do the same thing and divide everything by m. So we get x double dot plus b over m x dot plus k over m x equal to 0. Now we already know square root of km is omega n, right? Or omega n squared. Can we write this in a way that omega n squared can show up? If you remember from, I don't know what course exactly, but the second order systems, we can write their equation as x double dot plus 2 zeta omega n x dot plus omega n squared x equal to 0. I don't know, different MEs will see it in different class. What class you see it? Okay, so, and I know you could see different 3050, 3551, PSC, you probably won't see it. I don't know, physics. So now how did we go from here to there? Because that's the general equation of motion for second order system. If we can put this in that form, then we know the response. There are 3 different responses. We exactly know how our system behaves. So that's the idea. So we already know this is omega n squared. Now let's see if we can find something for Bm. So if we say B over M times 2 omega n, divide by 2 omega n, so basically times 1, right? And we can say 2m omega n times 2 omega n. Let me write the subscript smaller. All right. We call this zeta, or damping ratio, natural damping ratio. So natural damping ratio, not ration. And then we can say 2 zeta omega n. So I can replace this with this. Hence, we get that form. So if we have the equation of motion of our system, you're still not talking about control, right? It's the review. If you have those coefficients, you can actually find natural damping ratio and natural frequency of your system by just looking at it. Or if you have a system with mass m equal to something, and friction of something and k of something, you can find the natural frequency of your system. It is important because when you design your controller, you don't want your closed loop frequency to be equal to your system frequency, right? Because resonant, right? You don't want to get there. So I said that when you have this form, we know how the system will respond. The system will respond in 3 different ways, and it depends on our natural frequency. You already might know this, but just again, as a quick review, if zeta n is less than 1, your system is going to be oscillatory or underdamped system, and you saw that your system behaves like this, but then it can go to some steady state. You could have unstable system. You're not talking about the unstable system. I'm talking about when the system is stable, but it behaves differently. For zeta n equal to 1 means that your 2 omega n is equal to b over m. This system, you're going to have critically damped. And then for zeta n greater than 1, you're going to have overdamped. So that both of them are very fast. This reaches where you want quickly. This is not, has some steady state where we get rid of that. So these will be the three response of our system if the system is stable and reaches to equilibrium, right? Or to the point that we want. If the system is unstable, then you have different kind of responses. For example, you could have something like that. You could have, I don't know, sinusoidal, things that don't arrive to any final destination, let's say, all right? So your class participation is going to be finding natural frequency and natural damping of a system. It is important because yesterday when we developed our PD controller, we ended up having this equation, right? This resembles what we just had. So x double dot 2 zeta omega, not omega n is not zeta n. X minus xt, what was this? What is x minus x desired? Error, right? And omega squared x dot, the velocity. So now omega squared is going to be your kp, position gain divided by m, and that's your closed loop frequency, your system plus the controller. Here also your closed loop damping ratio is going to be this. So when you are analyzing the behavior of your system, when you draw this in MATLAB or wherever, when you are looking at it, you have to draw a closed loop system and see how your system behaves, including controller. So on an uncontrolled system, for an uncontrolled system, for example, your TS, your settling time is going, let's say 5 seconds. You want to control it such way that it arrives to what you desire faster, let's say 1 second, right? So you add the controller, you draw the response and check if it is 1 second now. That becomes your requirement for your controller. Means if your control is fast enough. You usually get requirements when you have to design a controller. So there's always this. Make sure this arm, design a controller that you go from any point to a X desire to pick up this water bottle, right? So I start from anywhere and I have a position. In your schematic, I have to go get that, right? But then how fast I'm going. That is part of your desired control design also. And you have to be given or you have to ask. If it wasn't, then you have to look at other characteristics of your system. All right. That's the difference between doing things on the paper and doing things actual work. If things work or not. If you have actual DC motor, actual actuator, you have to think about a lot of other options around, not just, oh, from MATLAB, I know my PNG is going to be this, like 1500 for KP and like 100 for KP. You're going to just blow up the motor if you do that. All right. So both of them were a review from what happened yesterday or generally background. Now, how do we select our gain? We usually, if you have worked with PID controller, which one do you start with? Austin? You start with P, right? You add the P, and then you look at the behavior of your system, see how it changed. If P wasn't enough, what do you do next? If you were going with PD control, which usually we go robotic, then you will change, you will add the value of D, KD or KD, they're equal. Interchangeably, you say KD or KD. Then you will have to tune these two. So now, if you have your system, we have a quick way of starting our first guess, right? Because PID controller tuning is try and error. You don't get the first number right away, but it's a good start. If you start from Kp equal to m omega squared, this omega is the closed loop frequency omega, right? Then your Kv becomes m times 2 omega to zeta omega. So first you have to set your zeta omega, which is the desired behavior of the system. Then from there, choose Kp, then from there, choose Kv. Because Kp might be sometimes enough. P control might be enough. Cars, what are vehicle users on the water vehicle controller? Cascaded P controller, bunch of P controller, right? So you don't have to always have the other I or D of a PID controller. It's easier to tune one parameter, even though if cascaded and you have multiple of them. So now we can use a little bit trick. So for our multi-body system, for an arm, right, we can say, okay, let's not assume the mass. Let's design everything for massless or unit mass, not massless. Unit mass system. And since the mass of your rigid body is fixed, you can always scale your controller with whatever mass that you decided that link is going to have, right? So you're basically designing a controller that can apply to different links, right? Because the only difference is if you use the same motor, the only difference is the link is longer, it's heavier or shorter or different material, right? But the mass will be different. So if you design for a unit mass, then you can just apply that controller and scale it by n. The only difference will be Kp is just omega squared and Kv is 2 zeta omega. And if you have, so this is the mass equal 1, that's what unit mass means. And for M mass system or multiple mass, then you can, so you're designing that Kp prime or Kv prime, and they can multiply it by M at the end, when you want to look at your final system. All right, so here scaling by M, and here first choose Kp, then choose Kv. So when we say first choose Kp, it's not like, okay, choose Kp and 5 minutes later choose Kv. Choose Kp, look at the behavior of your system. If you couldn't tune, then add some Kv to it. All right. So P or PD control, either one works. Any questions so far? Most of you should be familiar with most of these things. I know that some of you just taking control, so hopefully you are also and discussing control, so it should be fresh. All right. So we could use control partitioning. One of the techniques that you can use, basically designing a controller for unit mass and then scaling by n. That's what control partitioning means. But you're defining one control law for different similar systems, right? So if mx double dot is f, then if you can say that if you factor out m, then m multiply 1 times x double dot, so the unit system is mf prime. So f prime now is a control law, which is for unit mass. So f prime, so is f is equal to m x double dot, then f was our control law for a system with mass m, then f prime would be negative Kp prime. So I'm using prime to show you the difference, right? Then here, this is going to be omega squared and, sorry, you have to put it in the actual form. So 1 times x double dot plus Kv prime x dot plus Kp prime x minus xd equal to 0. Now, because we are dividing, because m is 1, we're basically dividing by 1. So this is our 2 zeta omega, and then this is our omega squared. You see that we don't have to divide by m because m is 1. And then you can multiply by m once you have it. All right. So this is when we have a linear system and we modeled it by massive spring, and then we decided either P is going to be the controller or P. But we know that most of our systems are nonlinear, right? How do we introduce a nonlinearity into our controller? Using the same method. So we are using equation of motion basically to develop our controller, right? Based on how the system behaves. Now the system is behaving nonlinearly. How do we count for that? Do you agree that the system might act nonlinearly? Oh, what happened?
Yeah.
It should be how? Can you bring an example? Can anybody bring an example? How? What's the nonlinear part of it? Maybe I should not show you that. I mean, it's fine. You can see that. Yeah, whenever you have sine cosine, or if you have x dot, you multiply by another x dot, right? Or if you remember, you had centripetal forces, right? So q dot 1 times q dot 2, that's nonlinear, or you have sine cosine of something, shut it off. So one example that should hopefully show you that nonlinearity, if I can draw it properly, is let's say we have a joint, a revolute joint, rotates this direction, which means, right hand rule. If I have a link connected, so that's the part that I might fail drawing, even though I have the appropriate education, because I've done this many times in my undergrad, and I did not like it. So let's say this link is connected on top of the revolute joint. When the revolute joint rotates, this link is rotating, right? So this link rotates here. I'm just going to show that this link ended up here. All right. But this is happening in the plane. Now, when we are developing our equation of motion, we have to consider for gravity, right? In this case, mg times, let's say r or L, whatever this distance is, remains the same throughout this motion, right? MGL does not depend on anything because we are rotating in a plane. Agree? Now, so this is linear. Still, we don't see nonlinearity. Now, let's change the direction of our rotation, the z axis. That's why configuration is very important. Let's say that this was the direction of our z. And then this is pendulum, right? Very. So if we rotate this way, so let's say this is theta desired. Theta desired is going to be here, and the link is going to get here. So this is rotating this way, right? Now let's look at the gravity. Now we have nonlinearity in our gravity, right? It was not even, it could be linear. Gravity could be a linear function depending on the way that the system is moving, right? So we introduced nonlinearity here. Now what do we do? For the controller, system dynamic, we can write it, no problem. But when we design our controller, we have to count for behavior of our system when designing P or D. Now, how do we count for this? So we can go back to our, yes? Yes, there will be a nonlinear term appearing. That's the point. Okay, we will have a nonlinear term appearing in there. I see what you're saying. Now, to address nonlinearity in our controller, one way is we can use our control partitioning mx double dot plus some bxx dot, so that we say that whatever that nonlinearity is, let's say it's part of bxx dot, right? So if you sine cosine matrix, you will define it. Is equal to a control force. Now, we know that we can say our control force has two parts. One is your F prime, right? Which was for unit mass. Let's say if you have a mass, alpha is the mass, so alpha F prime is going to be the control force, the PD or P controller of your system without nonlinearity. Now, to count for nonlinearity, we can add a beta. That the beta has to be, we will define beta in such a way that will only oppose our nonlinearity. So we use the linear controller we have. We are going to define something, model nonlinearity to function or to expression or constant. If we can define a relationship that will control the nonlinearity. Then if we write our equation of motion, mx double dot plus bx x dot, this is our system. Then this is going to be our controller. If you wanted to show it block diagram, so this is our system. We have worked with that before. So we can say that, you know what, our nonlinearity could be something like this. Like a positive feedback. It's just in a feedback loop. It's not a feedback. This is a way to add. So you can say this is your b hat x double dot. So you design the control for your linear system. You see the effect of nonlinearity and change your controller for that. So this will be added, and then this is your mass, and then this is your F prime. So this is F. You created F here. This gives you X and X dot, depending on what you're looking for. Let's fix that before someone else get confused. So if this was, let's say R, then this distance going to be R minus R cosine theta desired. Correct? Huh? Times M, yeah. Why 1/2? This is, hold on, let me just do that. I'm gonna say this is R, so this is R cosine theta d, right? What's going on? If this was L, I'm trying to fix this so when you are looking at your lecture later, you don't get confused. So mg, then let's say is L minus R cosine theta d. The point was that this nonlinear term will show up. Yeah, it changed. No, length of the link, they changed that. Basically, the idea is that this distance. All right. So this is the nonlinear part. So we will introduce the nonlinearity to our PD control. Right, and then we look back if we are not at our desired point or set point or trajectory that we go back and run until you reach, but we don't mix it with our controller inside our controller. So that was how we developed, let's say, PD controller. Now, for control problem, yes.
For adding the non-linearity, do we like use the same type of non-linearity as the system?
Yeah, depending on what the non-linearity is. You can have friction, it could be due to the gravity, it could be the product of velocity, we don't know, right? So we introduce a term that we make sure that our controller is seeing that. So we adjust our P and D to get rid of the non-linearity, right? We don't design a new curve, a non-linear term in our controller. That's why you can't use just normal PID controller for robotic application because of all that non-linearities. Now, here was, okay, this is how controller is developed, but what do we use control for? In our robotic application, we have two terms. We are either set point tracking or trajectory tracking. You know what's the difference? Justin, what's set point tracking? Your best guess. You get there however you get there. It doesn't matter how, right? What's trajectory tracking? Okay, what else do you think will be important in trajectory tracking? Position you could see that as set point tracking for every point. You update every time, right? That could be set point. You just have too many points. Like you have a vector, they're all set point. If you're just looking at the position, that would be set point tracking. That's what Alec was saying. So let's say you have a specific trajectory, you're K3, right? You create a trajectory, you follow. What did you use? Only position of your end effector, right? And then you use inverse schematic and you solve it. So that's set point tracking. You just have a vector of points. Now, when we talk about trajectory planning, what else is important, John? The velocity, how fast you're going, if there's any change of acceleration, right? So that becomes trajectory planning. All right. Now, for set point tracking, we are gonna have an X desired. It's easier, right? You're just basically updating every point as you go. You create your path. So that's what path planning or path tracking comes into game. You create your path, you decide, and you say, okay, my path generated this many points. I'm only interested at every point. So I update constantly what point I'm getting to, and however my robot gets there the best, right? So if there's obstacle in front of it, you can avoid it, you can hit it, you know. Everything else, you don't really care. Now, for set point tracking, our control will be, our F prime would be negative K V prime X dot. We didn't care about the velocity, right? Minus KP prime. So I'm using prime because these are unit mass, right? You can always introduce and scale by n. X minus X desired. So the error is X minus X desired. That's the only thing that shows up. That's the only thing that you read from your feedback. If you have a sensor, if you have a model, and that's what you control. You didn't introduce anything about velocity. So that's what we have been working on so far, the position control. Your control loop system, when you close it, when you put your controller and your system together for our unit mass, X double dot KV prime, X dot plus KP prime, X minus X desired. This is what we have seen so far. Now, if I want to show the block diagram of this controller and my system, I'm gonna have something like this. So let's say this is my system, and then let's say we are using a PID controller for a controller, right? So you can have KP, you can have 1 over S and KI. This is your I controller. And this is a block diagram way of showing PID control. So there's two way, right? Equation of motion, block diagram, you can also use transfer function. They're all the same, they're all the same. So this is your controller block that before you would say controller. Now we know what's in it because we decided we're gonna use PID controller, right? Then, so here error is generated. I'm sorry, I don't know what that happens. I think because this thing is on the bottom. I'm gonna put it here. And then I have X desire, my reference I'm feeding, and here X is generated. I'm feeding negative, and that's my controller, right? So if you decide P and D, well, obviously the second one in the middle, the Ki will be 0, right? So that's the structure of your PID controller. You can just give the coefficient 0 and then you eliminate them from your controller. So if you're using MATLAB, which I'm a big fan of using MATLAB for at least development and then learning or finding the control law, you can use a block, PID control block, and then use the values. So this is for your set point tracking. Now, if we had trajectory planning, trajectory tracking, then the problem will be slightly different. In trajectory planning, you're gonna have X desire, X dot desire, and X double dot desire, right? You could have either of them, all of them, or at least 2 of them. Now, if X double, so now that I have all 3 of them, what would be our control law? What is our F prime? Can anybody guess? Yes.
Is it like this? Every time you just see like X double dot, it'll be X double dot minus double dot desired, and then X dot minus X dot desired, and then X minus X desired.
So can you start from the X double dot?
Like it would be the same as the closed loop system above, except instead of X double dot, you have X double dot minus X double dot desired.
So you're so think about it. We are designing our controller, right? So X double dot is your system, right? But I understand what you're saying. I'll explain it. So it will be X double dot desire. X double dot comes from your inertia of your system, right? And then plus or minus here, because it is opposing, minus KV prime, now you're right. X dot minus X dot desire minus KP prime, X minus X desire. That would be your controller, all right? Now your closed loop system now is X double dot minus X double dot desire plus KV prime, X minus X dot desire plus KP prime, X minus X desire equal to 0. Now, if we say X minus X desire is our error, we just wrote X double dot, E double dot plus KV prime, E dot plus KP prime E equal to 0, right? Now it makes sense. Now it is what you were trying to say. So now we converted that to the aerodynamic, right? And we already went over how the response of our aerodynamic is. You want to make sure you start from some error. You want them to get down to error of 0 or whatever our desired error is. Sometimes you cannot get to 0. Maybe 0.001 is enough for you, for your system, right? So I missed. Yes, I did miss. Thank you. Yeah, this is important. We can mess up because this would change the definition. All right, so this is our trajectory planning or tracking control law. Our equation of motion becomes like this. Now, if I wanted to show the controller here, now you see that this makes sense for you. Like, okay, X minus X double dot, I'm probably reading the velocity from the output and then compare, right? But how do you define this? X double dot is not an error. You know what you're doing. No, you're not sure, or you have a guess? Anybody has a guess? When you have a positive value in your controller, that's not depend on your error. You know what that is. I'm not expecting you to know, I'm just asking to see if someone knows. Have you heard about feed forward, feedback controller? This is feed forward. You're feeding forward an acceleration to system, right? So sometimes when we design a controller, part of our control is feed forward, all right? So for this example, for this specific example, X double dot is our feed forward. The other two are in the feedback loop. Now, see how it changes the block diagram. It is important to understand block diagram because you can draw them, for example, in Simulink and then tune your controller right there. Or you can write the transfer function or state space, either way works. I'm gonna use a separate page because last time I tried this, I ran out of space. Okay, system here. And then let's say I'm looking at velocity and position error, right? X minus X dot, X desired, X dot minus X dot desired. So I'm gonna put both of those output out of my system. So there's two output coming out. I'm looking at two output at basically X and X dot. And this is gonna be that controller F. How the controller is made. The controller is made by, well, there was an M, there was an F prime, right? We develop everything for the F prime. So F prime is X double dot minus KV X X dot. Let's create the feedbacks first. First of all, my system needs B X X dot if there is any nonlinearity. I'm going to create that. That's going to be added to my system. So that's just parallel. It might also be from the position. I don't know. So I'm going to add both of them. The nonlinearity could be from the velocity or from the position. Then I'm going to add my controller for X minus X desired. So I know that I need a KP prime. This KP prime needs to get X and have to compare with X desired, right? So this has to be X desired, reference, comparing with my X. So that's, so far F prime is X desired minus X or X minus X desired times KP and goes into my system. So I have KP control, P control, and I have to create the D part. For the D part, I have to get a signal from my X dot, and then it has to be fed to my F prime. I'm gonna add, since I'm introducing another part to my controller, this plus. So I'm gonna add this guy over here. KV. So there's X dot desire, right? So that is being compared. So far I have X dot desired minus X dot multiplied by KV go to this F. I also have XT minus XZ times KP. So I created the two error parts. Yes, X minus X desired.
Sorry, X dot minus X desired.
Oh, X dot minus X desired.
Yeah, that one you have X desired being positive with X dot.
So here XD goes with positive minus X. Here X desire minus X goes here. You could flip depending on, it doesn't matter, you can't write, so because this is our reference point, this was the positive. So the way that you mean that why I wrote it like that up there? I assumed that my X was larger than my star, so I wanted to create a positive, doesn't matter. You can flip that, it's just be a negative sign or positive sign, right? Because it really depends on what your X star and X are. This could be a negative and then you can replace it. Just that is the difference. You're finding the difference between the error and the signal. Now, how do we show that feed forward part? I did run out of space. Okay. Now the feed forward part, show it with green, is gonna go directly to your F prime, would be X double dot desired. You feed forward it. If you need it. If you had any required acceleration, you can accelerate your system, then see how the system behaves, and they can modify it. You're not comparing it with anything, you're not multiplying by anything. Directly, whatever reference you have, you send it to your system. You're not amplifying it, you're not comparing it with anything. Copy forward. So for example, an application underwater body. For a lot of, so I don't know, you have seen the drone that I designed with my team. The drone has to go from the top of the ocean, let's say 100 meters down. And what it does, takes water in, becomes heavy, buoyancy, and weight. It just has to go down all the way. We don't have to do anything. So that's the feed forward part. Take this much water in, create this acceleration, and let the system go for, I don't know how many, depending on how fast it is. Let's say for 135 seconds, right? Or whenever you hit this pressure. So you go down, and this is feed forward. You're not checking anything. You're going until, based on whatever you set in your system, after this many seconds, or you're checking the pressure on the side, right? It is not because of the feed forward, it's not in the controller. You're just making sure you hit that depth. You hit 100 meters underwater, then you're doing something there that you need your actual controller there, right? So this is the feed forward part, and then you might have to do another task when you use feedback. So you could have different controllers in your system, they do different things. So that would be one application of feed forward. You just give a feed forward push, acceleration, whatever you want to call it, to your system. So nothing is being measured, it's just adding a force to your system. What time is it? Okay, we're almost out. Okay. So I got into just above the example. So we'll solve this example Monday. Hopefully makes sense. If you want, I will post this, you can go ahead and check. You're supposed to design a PD controller for this spring mass system. Okay. If you wanted to go ahead, you can check the solution. I need